Before we get started, let's have a look at the Danny Pig website. It's the YouTube channel, and you can simply find it by searching for Danny Pig 6354, or even these days, if you search for the title of any of the seminars, YouTube should direct you to my channel. Upon the channel, there are a number of playlists. We've got the Deep Thinkers website for a separate meetup group that I have. We have the CPD webinars for structural engineers in full, and we have extracts from those for the Mathcad. There's Mathcad files in there. We've also got a thing that I call the Piglet files, which doesn't quite fit into the full seminars and not Mathcad. So it's little examples of software, usually for software demonstrations. And my little side project is Big Pig Music. So I've been seeing what AI can do. So I throw some lyrics in and generate some music. They seem to be reasonably popular. So welcome to another graduate CPD seminar for structural engineers. This time we'll be talking about steel portal frame design to the New Zealand code NZS 3404. And we're looking at various tools, including Multiframe. And yes, we'll be looking at our Redco spreadsheet very briefly and wondering what it does. And I'll give you the solution using Mathcad. So an overview of the contents for today's presentation. We're first of all looking at frame analysis, drop into a thing called Klein-Logel, look at some Mathcad for that, a brief word on second order analysis, and then jump into Bentley Multiframe. We'll then move into frame design, and we'll see what our output is from the Bentley Multiframe analysis. See the steel design report that Bentley Multiframe puts out. Then we'll look at moment modification factors, restraint factors, and the Redco spreadsheet, and eventually into the Mathcad in great detail. So Adolf Klein-Logel developed a series of books, this one in particular, looking at beam analysis and frame analysis, and it compiled charts for different types of frames. And this is how we did frame analysis before computers came along. Basically, you would look up what type of frame you had and what type of loading, and the little formulas at the bottom would allow you to derive the moments, the reactions, and the shears, and so forth. And because you were going to do elastic analysis, you could put them together with the principle of superposition to get your full set of bending moments and shear forces for your particular frame. So here's one way of putting it into Mathcad. So here's the Mathcad file for some basic frame analysis, and these are the formulas that we get from the Klein-Logel tables. So you put in the basic information and length of the frame and the height of the frame and the second moment of areas of the rafters and the columns, for example. Notice we haven't got an E value in here because it's assumed that the E value is constant as well. So you derive the coefficients from the Klein-Logel tables, and from that, depending on what kind of loading you've got and what kind of base support you've got, you can pop out the support moments in accordance with the formulas given. So it's a relatively quick way of analysing a frame, and you can do it for different loading patterns, and you can also do it for different base arrangements. So you've got pin bases, the bending moment diagrams are slightly different, obviously no moment at the base, and your formulas pop out the answers for the bending moment and shear forces and reactions as well. So that was a nice, quick and easy look at how you derive the basic moments in a portal frame. A quick word on second order analysis, and this will pop up again when we look at Multiframe. So there is no really quick and simple way of knowing whether you need to do second order analysis. There is a very long and complicated formula that tells you whether your frame is sway sensitive. And if your frame is sway sensitive, then you need to add moments on it due to deflection. So if you can imagine a frame that moves to the side, the load that you're applying, and we say P1, is no longer where it was applied. It has moved across. So you've applied it now with an eccentricity, and this eccentricity then amplifies the moment. So you start with your first order deflections, and then you do the analysis again at the displaced position. And this is known as a second order analysis or a P delta analysis. Happily, Bentley Multiframe will do your P delta analysis. There's also a P little delta analysis, which is about the displacement within the member. So the P big delta, as we like to say, is about the overall movement of the frame. So as I say, there's no quick and simple guide as to how you know whether your frame is sway sensitive or not. And Bentley Multiframe won't tell you until you start doing the design. It'll happily do a sway sensitive frame, give you all the bending moments and shear forces for the analysis or first order elastic analysis for a sway sensitive frame without telling you that you need to do a second order analysis. It's only when you come to do the design that says, oh, you need to do a sway analysis. And so we jump into Bentley Multiframe. Most of you, I'm sure, are familiar with it. So here is my example of a portal frame with a prop in the middle. This is quite a long span portal frame, so it's quite often we put in a prop in the middle. And in this case, it really is just a prop. There is no moment connection there. So this makes the vertical load carrying capacity quite a bit bigger, but your lateral load carrying capacity is no bigger at all. So if we put a 3D render on, we can see the different frame elements. So our stanchions and our rafters are made up of the same 460 UV section, and we've got a little 200 UC post in the middle. So we'll have gone through and applied the loading in various load cases. In this case, it's just gravity, live loads, and then we've got wind uplift, wind down, and earthquakes applied as point loads to the eaves. We can go into analyze and we can do the linear analysis. I've already done that, so let's look at the results. And here is the bending moment diagram for this particular load case. If you want to do the envelope load case, it looks very complicated because you've got multiple layers. These are bending moment diagrams for each of these load cases. If I look straight on at it, because it is a two-dimensional frame. So we can see just from this, by the magnitudes, the largest moments are going to be at the eaves and at the apex of the frame, which is quite common. And the color coding will give you what load case you're looking at. So if I pick out the particular ones, this is the load combination for gravity loads, and then we can click through it in the different load cases. So this is wind up and this is wind down, and so forth. So that's the analysis. I'm sure you're all familiar with how you analyze in Multiframe. The more complicated part is the design side of things. And first of all, on the design side, you need to check that you're using the right code. So in our case, we're looking at NZS 3404. Okay, so we're good to go on that. You can select either part, do it by each individual member, or if you want to be quick, you select the lot and go a quick design check. Now I'm doing a check, not a design. So I've already put in the sizes of the members that I'm using. I'm not getting Multiframe to actually design it. To do that, you click on the design. So let's click on the check. By default, it gives you a check everything. I don't normally check serviceability because I do that as a separate check. If I click OK, it'll run through the design checks, and we go up to our resultant pages. You can see here are the displacements, here are the reactions, member actions and max actions, and so forth. right over on the right hand side, there's a tab marked Design Efficiencies, and we can see that from our simple frame we've got our design efficiency. That is the applied load versus the capacity, and we can see that our column marked as number 4 is at 96% capacity in there, and the governing load case is the wind uplift across the building. I like to present a concise version of it, so I use Excel to cut and paste selected items from the multi-frame output. So here is my design summary, and in this case I think this is for a different frame or a different load case, because I've actually done a P delta analysis with this one. So we'll come on to that in a moment. The P delta analysis increases the moments, and your design efficiency number goes up in each of these cases, and you see the gravity loads are becoming more significant as we do that. And similarly, I cut and paste the member actions. I've got one set for the linear analysis, another set for the non-linear analysis, simply with reactions. I've got SLS reactions and ULS reactions as well. So that's a neat way of getting from multi-frame into your calculation report. And here is the steel design report. I've done a very brief one from multi-frame for that simple frame. It's a mere 12 pages because we're only looking at number of members, a limited number of members, and a limited number of load cases. If you select every load case and every member, your design report that you spit out, even if you only want a brief output, ends up as hundreds of pages. So let's look at this. This is the design report from Multiframe, and you can see we're checking design member number 1, which happens to be a column. It's got the section type, section dimensions, and the section properties, all relatively straightforward. It's put in the design parameters, and then we check against each load case. This is a load case for wind uplift up at the ultimate limit state, so we're checking for strength. So it's taken what the design action is. So our maximum bending moment about the major axis is 56 kilonewton meters in this case, and so on. And we've divided, well, we haven't divided them segments. We've got one segment for the full height of the column in this case. And it derives the member capacity about the major principal axis. The simple member capacity, which is based on the section properties, i.e. the section modulus multiplied by the yield strength, comes out as 444 kilonewton meters. So that's the basic strength. Now let's look at the buckling, and it needs to pull out a reference moment. And again, we'll come back to that in the Mathcad in more detail. And it derives these parameters alpha S to modify the moment that you can apply. So your buckling moment capacity is now down to 319, and this is for the column. Again, it then checks the minor principal axis. It checks the shear, as we've seen before, and then it checks the compressive capacity, simply the reduced effective area multiplied by your yield to give you a quite large axial capacity. Checks the tensile capacity and so on, and then checks combined actions. Then at the end of that gives you a member capacity summary, and then the checks. It compares the applied load that is derived from the analysis and compares it with the capacities it's just calculated above. And off it goes. It does the whole thing again and again for each. So if you like to wade through that, you can. And this is the brief analysis. It's a much more detailed analysis you can put out. Just a mention on moment modification factors. So this is alpha M, which appears in table 5.6.1 in the code. And the code isn't very clear, and so I've pulled out a nicer diagram from a textbook. And so the moment capacity of your beam or your column or your rafter is dependent upon how you are loading it. And so that the shape of the bending moment diagram, as you can see here, will give you this modification factor. So the simplest we start with is you've got a moments at either end, and if the moment at one end is just the same as the moment at the other end, then our beta m is -1 and our alpha m is 1. Notice it's minus because it is expecting this, which is double curvature bending. So when double curvature bending, your beta m is going to be positive. If it's single curvature bending, your beta m is going to be negative. And the beta is always going to be the smaller version of the difference in the moments. And you can pop through the equations for alpha m, which we can use later. So there's a range of load situations and end conditions and support conditions you can look at from the table and pull out the value of beta m, which gives you the value of alpha m, your modification factor to use in the equation. There are also restraint factors as KT, KL, and KR, which are given in the tables. So we start with our twist restraint factor, KT, which is given in table 5.6.3. So it's the restraint conditions at either end of the segment you are considering. So F is fully fixed, U is unrestrained, and L is lateral restraint. But to complicate matters, they've got something in between. P is partially restrained, and as soon as you start bringing in partial restraints, your factor is slightly different. You've also got the load height factors, KL, for gravity loads. And within the segment, you have different numbers depending on how the load is applied. Now, because you've got a rafter that's supporting purlins, you would think that your load factor would be 1.4. However, CSOC have said that you can use 1 simply because your top flange is not able to move if it's got a purlin attached to it. In there, the 1.4 is situations where your rafter can move with the load or your beam can move with the load, and the classic case of that is a crane rail. So if the load imposed on the crane rail will cause the rail to move laterally, then you need to increase that KL factor. Third K factor is for rotational restraint, and again we've got these rather cryptic notes of F and P and U. So the KR values are always less, either 1 or less than 1. So you can be quite conservative and just say 1 in those factors. So there are some diagrams in the code, but they're a bit, shall we say, not very clear in the code. So I've borrowed some images from a textbook which make it a little bit clearer as what do we mean by restraint, lateral restraint and full restraint to our beams. So here is the example for a beam. If you've got a concrete floor on top of a simply supported beam, your compression flange is up at the top and that's going to be fully restrained. So you shouldn't need to worry about lateral torsional buckling in these cases. If you've got a more open frame, you may be attaching other members to it, which will prevent compression flange from distorting laterally. So full restraints for beams. So So we're looking at the critical flange. So usually it's a compression flange. If it's simply supported, it's going to be at the top. If it's a continuous beam or a member of a portal frame, your compression flange can either be at the top or it can be at the bottom, because we'll often have double curvature bending. And so we'll have what we call fixed end moments at the end of the members. And so if your compression flange is down at the bottom, you need to apply some restraint to that. And here are some examples of full restraints to the critical flange. Here are some partial restraints, and there is some debate as to what a partial restraint will actually mean. Now, this one on the bottom left is quite interesting, because in this case your critical flange is at the top, so it would appear to be unrestrained, but your other flange is fully restrained. Now, by virtue of your lower flange being fully restrained, you have some restraint, and there is a number of tests on how restrained your compression flange is in this situation, and it really depends on the section. The stockier your section, the more restraint you get. If you've got a slender section in here with a long skinny web, then your compression flange is unlikely to be restrained at all. Just as a guide, the old RSJ sections are generally quite stocky, and so you often have quite good restraint to your unrestrained flange. Lateral restraints for beams are relatively straightforward. I'm just stopping that compression flange moving out of its position. Rotational restraint, so we can add stiffeners in certain situations and positions to stop the beam rotating about its own axis, its own longitudinal axis. And here we come to the Redcoat spreadsheet. I won't go into too much detail on this, but we have some basic information to put in. You select the section you wish, put in the effective lengths, and don't forget to change the K factors. More importantly, have a look at what's going on over here, the bit that doesn't print, and the M1 and M2 and betas are all there to be changed to give you the correct values. So now we come on to the Mathcad, and this is the big heavy one. This started way back in 2020, but has since been obviously updated primarily for this presentation. And there was a voice in my ear that kept going, what about? What about this? What about that? So here is the Mathcad for the steel portal frame design check, and we're checking for bending, shear and axial load of our frame members. So we begin with a summary of the analysis results we got from Multiframe. So for each of the load cases here, we've got the 1.2 dead plus a 1.5 live, and following a P delta analysis. And our maximum moments, shears and axial forces are given here. And we repeat the exercise for our wind with dead load down, and then we have wind up with our minimal dead load. And these are the moments, shears and axial forces for that. So that's a summary of the loading that you're putting on the frame. Okay, so we start with the rafter check. So our rafter span is 20.7 meters long, and we're looking at the loading going on that rafter, and we picked out the numbers from above to give us our maximum axial load, shear and moment applied. So we put in some basic information for the rafter. We have a Young's modulus E as 200, shear modulus G is 80, and then our strengths, yield and ultimate is 304.30. Our strength reduction factor for our members is 0.9, and that's taken from the table. So we pull out the section properties from the rafter, and Steel and Tube provide full data tables from this. You can just copy them over. Similarly for all the I values and Z values and S values. So the elastic section modulus and the plastic section modulus you're looking at, and in particular the radius of gyration about the major and minor axes. The steel and tube catalogue also tells you what the form factor is, so you don't actually have to work it out. So moving down, we pull out our slenderness parameters, and this is looking at clause 5.2.2.1 in the code. And then we compare it with the limits given in table 5.2. And for our section classification has come out as compact. For anybody who's used to Eurocodes, this is slightly different from our Eurocode classification, where we had a much larger range of section classifications. So we begin with a basic bending check for the rafter, and we look at the section modulus, and we look at the section moment capacity elastic in this case, so 444 kilonewton meters. So if it's fully restrained, the section capacity is going to be 444 for that beam, and putting on a strength reduction factor, we get a capacity of 400 kilonewton meters. We can do the same exercise for a minor axis and come out with a bending capacity about the minor axis of 68. So we can compare the section capacity against the applied moment, and we're still good. We're 91% now, so we're quite close to the limit on that. If we'd failed on this, we need to start again. Basically, our section isn't big enough. And that'll save you the time for the rest of this, because the rest of it gets a lot more complicated. So we're looking at buckling, and it's buckling about the minor axis. So your major axis capacity for a rafter depends upon the buckling about the minor axis, and the minor axis is restrained along the length of your rafter. So you've got a 20-meter long rafter, but you want to divide it up. Conveniently, we have purlins at regular intervals, and the little trick is to double or halve the space between the purlins at the eaves and the apex, and that halves the effective length that's unrestrained. So we've now got a length between the restraints, so we've got 1150 millimeters between our restraints. We look at the moments at the ends of that section, which is 362 at one end, 255 at the other end, and this gives us a end moment ratio, or a beta m, as 0.7. We can plug that 0.7 value into the equation given in table 5.6.1 for our style of loading, and that points out a alpha m of 1.16. We can just check that are we restrained or unrestrained. Now, given those values, it turns out that this section is actually restrained anyway, so buckling shouldn't be a problem. I've conservatively put in the KL as 1.4, although it could be 1, as I discussed earlier. So the effective length of my segment is 1.61. A reference buckling moment taken from the equation of 5.6.1.1, and the sharp-eyed would notice that this bit is the Euler buckling value for axial compression on a strut. Then we add the torsional buckling value, and we derive our slenderness reduction factor based upon that reference moment, and we compare it to the capacity, and that spits out an alpha S value of 0.938 with a nominal moment capacity coming out as 482. Now, that's actually bigger than the section capacity. And if you remember Euler buckling, you'll notice that the strut curve actually goes up way past the yield capacity and never actually reaches the y-axis of that Euler buckling diagram. So we take the minimum value for the buckling moment or the section capacity moment, And so we're looking at a design bending capacity of 400. Okay, that's relatively simple, honest. There is an alternative method given in the code. It allows you to derive the alpha m from this equation here. But you need to know what the moments are along your segments. So remember, your segment is the length of your rafter between restraints. And so if you zoom in on your bending moment diagram, you get the moments on either end, and then you want the moments in between. So your M2 is the bending moment at the quarter point, M4 is at 3/4, and M3 is the one in the middle. Now I've cheated a little here because I've assumed I've got a linear distribution of bending moment between the two ends. In reality, it won't be, it'll be slightly different. But for the sake of this exercise, we can use a linear distribution. So our moment modification factor alpha m spits out through this equation as a 1.149. And our alpha s, again from above, and then our moment capacity pops out as 478. It's slightly different from above, but quite close to it. So the two methods give you similar results, but not exactly the same. But again, in this case, our section capacity dominates. Now, if that was the worst case, you could stop there for your bending and buckling capacity. However, as we've said, for maximum efficiency, you halve the spacing between the purlins at the eaves and the apex, because that's where the maximum moment is. So we need to look at the next section, and we pick out another section, and the length between the restraints is now 2.3 meters. And we go through the same routine again, find our reference moment, and we actually I've actually put these in from the bending moment diagram given by multi-frame analysis. And that pops out our maximum moment. So the MN is the maximum moment. It's not the end moment. It's the maximum moment in that section. And that gives you an alpha M modification factor as 0.995. And that spits out your design bending capacity of 285. Now we're comparing it with the maximum moment applied. So the maximum moment in this section is less than the previous section. So therefore our maximum moment is smaller than our capacity, which is okay. Right, so that was bending and buckling. Now we need to check shear. The first thing you need to do is check whether your web is stocky or slender. And we use that equation from clause 5.11.2.1. And we find our gross sectional area of the web multiplied by the yield and with a 0.6 factor applied. So our nominal shear capacity is 694. Put in a strength reduction factor, and we find that we're only 15% used. Okay, now that's straightforward shear capacity, but you might want to look at the shear buckling capacity. So slender webs, this isn't a slender web, but if you have a slender web, you need to check shear buckling of the web. So your alpha V, again, is coming from the code equation, and it comes out as 2.2. This, therefore, is bigger than your standard shear capacity, which means you take the minimum of the amplified or reduced shear capacity and the straightforward shear capacity you've worked out before. So we stick with our 694. So that was shear. Move on to the axial load check for the rafter. We've got our form factor, we've got our effective areas. We allow a little bit less sometimes for volts. And we look at the effective length. In this case, it's 3.22. And we've got our effective length for the major axis as 1.2. And we can derive the slenderness reduction factor to 140. and alpha A as 13, again from the clauses in the equation. Because it's an I-shaped section, alpha B is 0. Different sections will have different alpha B values, so you've got to look it up in the table. We get a lambda as 140, multiplying those together, and eta of 0.415, epsilon as 0.789, and finally an alpha C derived from all of that above as 0.3. So we take that 0.327 and multiply by a nominal capacity of the section itself. So we get quite a large figure of 775. And so our applied load in the rafter in axial compression isn't that great. So therefore our utilization is only 16.2%. Then we need to look at a combined check. And this is telling me that there's a little test as to whether axial load is significant. And so if you're at 5%, if you're less than 5% of your capacity, then axial load is insignificant. In our case, it's slightly above, so it's still significant. So we need to check the combined actions. So we reduce the nominal section capacity due to the presence of axial load, and we check it against the values given in the clause, 8.3.4, as a combined utilization ratio. And again, we've got an alternative design provision given in clause 8.3.4, and you can combine the two factors together with our reduced axial capacity and get our reduced moment capacity there. And we then derive this gamma factor, and our utilization factor comes out not just simply the applied load divided by the capacity, but we factor it by, in this case, a 1.5. Happily, we're still under. This is the what about one. Now we've assumed we've got restraints to our rafters. Now, to show that the restraint has adequate capacity, we need to check the restraint. The force we're putting in is given by the code clause 5.4.3.1, and it just tells you that you've got 2.5% of the axial capacity in the compression flange. And we do a little trick to derive the compression flange capacity, or the compression flange force. You take the applied moment at the restraint divided by the depth of the beam, and then you need to add on the axial load and divide that by the two of them, because there's two flanges. A quick check on the rafter restraint design. Yeah, this is again the what about. Normally we would just put it in by eye, but just to be thorough and complete, we derive the design capacity of our angle restraint, and it's a 50 by 50 by 5 angle, and we can pick out the section details from the steel and tube catalogue, and then derive the axial capacity as we've done before, and that turns out to be 68 kilonewtons, which is well in excess of what we need. Just to check on the bolt, and we need to check the capacity of the bolt in single shear and apply that to the number of bolts we've got, in our case 1, and then apply a reduction factor to that, and we'll see our limitation is going to be on the bolt. Let's check the cleats. And so you've got a thin plate connecting your end of your restraint angle, and you've welded that to the bottom of your rafter, and you've come up with a capacity of 25 kilonewtons for the shear capacity of the thin plate, and the bearing capacity of the thin plate is 66. So both of those are good. A quick check on the welds, and our weld capacity of a 3mm weld, which is given a certain size. It's assumed that we've got welds at full depth of the cleat on each side, and the design capacity is 31. So again, okay. A quick check on the deflection you've got from the multiframe analysis. You've got an 80mm mid-span deflection, and that works out as span over 259. We'd normally put a suggested limit on your mid-span deflection of 250, so we're just within. Deflections and deflection limits in the New Zealand code are advisory. They're not compulsory, and they're way open to debate. And there's a lot of debate among engineers as to what the values should actually be for your member deflections. And the actual member deflection limits are really depending on what you're doing with your member. Okay, well, that was the rafter. Now we go through the stanchion, and here's the stanchion height. It's 1.4 meters long, height of our stanchion. We've derived the applied loads from our analysis. Our material properties and our section properties are the same as the rafter, so we just pull those down from above. A bending check for the stanchion. We've got a bending about the minor axis of 68 and a bending about the major axis of 444, as we saw before. Then we need to look in the buckling, and because we're going to restrain it with girts at third points, we can say that our girt spacing is 2.5, therefore our segment length is 2.5 meters. And the beta M value we can take from the table, because we're looking at the top third of a pin-based stanchion, and we've got an alpha M of 1.18, which gives us a max span of 1.4. So that would suggest that we add our rotational factors, our twist factors, our load height factors. That comes out as 2.1. So it's telling me that it's unrestrained and buckling might be an issue. We derive our reference buckling moment as we did before, and our slenderness factor as we did before, and come out with a nominal member moment capacity is 458. So which is higher than our actual section capacity. So we check for shear as we did before. So because it's a stocky web, it's going to be about the shear capacity rather than the shear buckling capacity. Then we need to check our axial load. So again, we look at the slenderness limits, and we can compare those with the effective width we've actually got. And from that, we can derive our nominal section capacity. You see that's 2,373 kilonewtons. So it's a very large axial load capacity. That's if it's fully restrained. If we go through and look at the two directions, so when you're looking at an axial load, you need to consider both directions, i.e. minor axis and major axis. So we have restrained it at third points, but we've only restrained it about the minor axis. About the major axis, it is still unrestrained. And because it's a sway frame, you get a KE of 2.2. So that makes a big difference in the axial capacity of your stanchions in a pin-based portal frame. So you work out your slenderness reduction factors from clause 6.3, and that gives you a nominal member capacity of 14 and 10. So the slenderness limits are based on the maximum slenderness you get from the minor axis or the major axis. Now, in some cases, because of the differences of restraints you have, the major axis may be the problem rather than the minor axis. But for most of our universal beams, and given that you're probably putting girts on your columns, you probably find that it's your minor axis. Depends. Again, looking at combined actions for the loading of the stanchion, as we've done before for the rafter. And we get to our final capacity. A quick look at the stanchion restraint. And we've got our restraint provided by panels, and the limitation is actually the bearing within the panel. So we need 4 bolts to connect our stanchion restraint to that column. Finally, looking at the deflection. Now, often portal frames, particularly skinny ones, are dependent upon deflection. They're almost governed by deflection at serviceability limit state. And we've gone originally with our pinned base portal frame design and found our deflections to be rather large. So there is a paper from the Steel Construction New Zealand report Gen 7001, and that talks about base fixity, and the base fixity can be partial. So sometimes you can go somewhere between fully fixed and fully pinned and put a spring in there. So for SLS loading, it recommends a value of 0.8 EI over H, which gives us a rotational stiffness of 6,387 kilonewton meters. So that gives us your limit there. Just faded out there is a similar one for ultimate limit state at 0.4 for ultimate limit state. The thing to note is if you are putting spring bases in, you are going to attract moment at your bases, and therefore your foundation needs to be designed for that moment. And there are not many simple pad foundations that can take the moment you're putting it in at ultimate limit state, whereas at the serviceability limit state, it can probably quite happily survive. So given that our portal spacing is at 7.5 meters and our portal height is at 7.4, the suggested limit on the sway deflection is the smaller 2 versus 200. So our limit is going to be 37 millimeters. From our multi-frame analysis with a spring base, we get down to 25 or 27 in the case of earthquakes, which in either case is quite adequate. So, quick note about our next seminar, which has yet to be written. And we're going to talk about stiff diaphragms and lateral load distribution. And we're looking at seismic actions and accidental eccentricity. So there's quite a lot in there. And yes, there is a Redco spreadsheet for this. Top view in this last month has been the last seminar, surprise, surprise. And second is one of the songs I've done on the Big Pig Music channel. The Genius of Thomas Sowell, my little extract there for Deep Thinkers, is showing a good return. And then we're going to the Mathcad files for the previous seminars. So wind analysis still quite popular, and the bronze method of pile design is there just as the Mathcad extract. And this one is surprisingly popular still. This was put up over a year ago, and it's still getting great. It's still one of the top performers on the channel.